Afternoon, everyone. Thank you again for joining the Cybersecurity and AI Innovation in Healthcare seminar series. We have our guest speaker today, Dr. Mukherjee, and the topic is going to be about AI-driven cognitive radio sensor networks, implementing distributed artificial for visually impaired individuals. Again, this abstract to the topic is an AI-driven framework for cognitive radio sensor networks that can assist visually impaired individuals in real-time navigation and environmental interaction. It's based on advances in 5G, wireless sensor networks, and distributed artificial intelligence. We're using the approach of machine learning and CRSNs to provide continuous environmental updates such as obstacles, traffic conditions, and other safety critical cues. And this will include a discussion on software-defined and cognitive radio platforms, distributed AI techniques, and their role in enabling energy-efficient, scalable smart healthcare and consumer applications for independent mobility of visually impaired users. We'll give a brief bio about our speaker, Dr. Mukherjee. So Dr. Mukherjee is a senior member of IEEE. He obtained his PhD from Kalinga Institute of Industrial Technology, University in India. He is currently working in the Department of Computer Science as a Faculty of Science for the University of South Bohemia and Siske. You may need to pronounce this for me, Dr. Mukherjee.
Yeah, České Budějovice. You can check it. You can pronounce it as Budweiss, as like beer.
Advice. Okay. Thank you. In the Czech Republic, he was previously a postdoc research fellow at the School of Computer Science and Communication Engineering in Jiangsu University in PR, China. Dr. Mukherjee has published more than 100 research articles and 5 international granted patents. He has also been a reviewer in many IEEE journals and other prestigious conferences. He was listed in the world's top 2% scientists in 2023 and 2025. He also served as a special issue guest editor for IEEE Internet of Things Journal, Computer Communications, Multimedia Tool and Applications, as well as the Journal of System Architecture, Computers, Material and Continua, Frontiers in Physics and Sustainability. He is also an associate editor for the International Journal of Interactive Multimedia and Artificial Intelligence and an academic editor for wireless communications and mobile computing. His research interests include artificial intelligence, next-generation IoT systems, wireless sensor networks, cognitive radio, and signal processing. Thank you so much for your time, Dr. Mukherjee. We look forward to your presentation, and the floor is yours.
Thank you, Asma. So let me introduce myself in a very separate way. As you all know, my name is Dr. Amrit Mukherjee, and I'm working with Department of Computer Science, Faculty of Science, which is located at our University of South Bohemia in Czech Republic, and the place is České Budějovice, as I've told you. So it's quite hard to pronounce. Anyways, I was quite interested with the seminar topics and the theme of the seminar presentation, and special thanks to Professor Uttam and Professor Pushpita for inviting me for this particular seminar. Somewhere I feel my research topic, my research team's work since last almost 8 to 10 years, it is quite aligned with the theme of the seminar. Okay, because we are working right now with the smart healthcare operations, we have got some recently some projects on smart healthcare. And my team is dedicatedly working with some AI tools, AI algorithms. We are playing with everything, almost everything, basically with the smart healthcare portion. Now, recently, I have been collaborating with several different teams in different part of the world, and finally, this is one of my recent publication, and that is why I thought like it would be very interest to present this particular paper or my research theme for this dedicated data science seminar. Now, the topic which I've chosen is AI-driven cognitive radio sensor networks, implementing distributed artificial intelligence model for visually impaired individuals. Well, so as you can see with the topic, there are several technical things. Let me try to be very simple in explaining. We have AI, we have cognitive radio, we have sensor networks, we have cognitive radio sensor networks, and finally the visually impaired individuals. So I'm trying, or my team is trying to combine everything to make a very impactful application with the consumer electronics forum. So let us start the journey from the first slide. So, okay, yeah. Now, this is basically the full system architecture. So here you can see everything is quite compact and it's in one place. So let's see with this particular block first. The environmental block presents the real world user navigates, as we can see, the obstacles, pedestrians, vehicle, traffic signals, road, building, etc. And somewhere we have to focus that our main theme is to go for the visually impaired individuals. Now, again, coming back to the first block. So here we have obstacles, pedestrians, and all the things which in daily life the visually impaired people or the partial visually impaired people they face. Now, basically, what we are trying to do is the existing system, as you all know that in the existing system, you have seen. Okay, let me go to the seventh block. As you can see, this is a visual impaired person, and he's having a stick, and his stick is having so many types of different sensors with which he can get the information like to go left, right, or to go straight, and all these things. But basically they are a reactive type of responses. So AI is not doing the reactive type of responses, rather it is improving the reactive type of responses. So what exactly is the the most important part of this particular seminar presented by me is the cognitive radio sensor network. So basically there if you can see you will find so many papers which will which will be combining the environmental thing and the visually impaired user thing, and the sensors they will be having the AI features. So what is the novelty? What is the state of the art? What is the research gap with which we can work? And that is where the area where I'm working right now is cognitive radio sensor networks that comes into the play. That is block three. So again, let me go in a very simple flow. So first, let us focus on the environment. So here we have certain things, obstacles and traffic signals, blah blah blah, and then finally these are being absorbed and calculated or stored in the sensor acquisition layer. So here they're in a stick or different devices, maybe a watch, maybe a hat, maybe some shoes. So they may be having cameras, ultrasonic sensors, lidar, GPS, and some different variations of sensors, a microphone, and all. So somewhere you will feel like yes, there are transducers, there are sensors, but what exactly is the theme with which AI can be implemented? So here AI cannot be implemented in a simple words. If you want to implement it with the data, so basically you will be jumping from 1 to 2 and then 7 directly, which is somewhere create a problem. I'll explain you how. So let us go from scratch 1, 2, and finally, with the input of the sensor and acquisition layer, we are trying to feed this raw sensor data to the third block, that is cognitive radio sensor networks. So to explain the cognitive radio sensor networks, I'll be explaining you in the upcoming slide. So cognitive radio is a feature, is something quite different, which is existing since last 10 years, but unfortunately, it has not been implemented yet in a practical scenario. But the thing is, how the primary users, that is the licensed users, they are they are doing all the stuffs, and the secondary users they are not able to accommodate themselves. those who are unlicensed users. So this is the play of the cognitive radio theme. So finally, continuing the same phenomenon for cognitive radio sensor networks, we are forwarding the same thing. So first, we are gathering the raw sensor data from data acquisition layer. That is, these are the devices, and some more may be possible. So we are trying to collect the raw sensor data. So after collecting the raw sensor data, what we are doing, we are trying to do the spectrum sensing, primary user detection, interference measurements, and spectrum availability map. So this is the foremost important part where we are expecting as a researchers that there should be as low, like the probability of false alarm should be as low as possible. The probability of detection should be as high as possible. So after gathering the spectrum sensing data, we are forwarding the same to cognitive radio controller. So what exactly the controller is doing? The controller is doing the dynamic spectrum access. That means the secondary users can see and can feel like, okay, right now I'm in channel 1, I have to go to channel 3 after 3 seconds. Or from channel 3, I have to go to channel 7, channel 9. So, and again, after 1 second, I have to switch back to channel 4. So these type of things the cognitive radio controller is governing. So it is governing the dynamic spectrum access. That is the dynamic spectrum access. The channel selection, power control. Power control means the way each channel in a single bandwidth, they have been governed and they have been given a standard power with a minimum power and the maximum power from the spectrum allocators. And now the interference avoidance and channel switching. So these are the last two terms which is very important for cognitive radio sensor networks. And we are forwarding the same knowledge, the same output to the communication and routing. So basically, if I'll explain you like what exactly we are doing is, first we are sensing the channel and what is available and what is not available. And based on that, okay, if this is available, the first secondary users will switch to this, the secondary users switch to this, and subsequently in every second or every milliseconds and so on. This is the 3.22 block. And finally, once everything's okay, we are going to communication and routing part. That is multi-hop routing, link quality estimation, reliable data, and energy aware routing. Well, 3.3 block is also important, but not so important because somewhere the things are more depending on 3.1 and 3.2. And 3.3 is responsible because the output of the 3.3 is this particular stick. If you can see on block 7, this particular stick, the output of this particular stick depends almost completely on the block 3.3. So 3.3 comes later. So overall speaking, this is a cognitive radio sensor network, how it works with the output of the sensor acquisition layer. Now, again, we are forwarding the same data to edge fog processing layer. So what exactly they are doing is they are doing the data aggregation, noise filtering, sensor fusion, feature extraction, and contextual data storage. So all these terms are quite, I think you have already studied all these terms. So somewhere I feel the most important part is the feature extraction, because with the help of this particular system, your stick will be able to find like in what type of road you are walking, what type of obstacle you will be facing, and that communication with the main server, which is completely, it is located somewhere 2 kilometers away from you, is been monitored using cognitive radio sensor network. So basically, what I'm doing is I'm trying to use a wireless technology which will use the unlicensed band in such a way that it will fuse the AI inside it. It is as simple as that. Okay, so we are happy with the edge and fog processing layer, and finally the processed features. As I've told you, like I've given some examples. These are being fed to the AI intelligence engine. So where we have to see, this is very important. We have to see the perception. That is the object detection, what type of object recognition, traffic signs, signal detection, So these are not possible, this 5.1, 5.2, 5.3, these are not possible by the generic sensors. Those which are available in the markets right now. As I told you, the sensors are quite reactive, but they are not AI driven. So somewhere we are trying to make it AI driven, as well as we are trying to fuse the cognitive, the intelligence. Cognitive is your intelligence, the intelligence radio sensor networks. And finally, after this fifth AI intelligence engine, we are focusing directly on the user side, the consumer side. That is the text to speech, like how it will indicate that particular person using text to speech or voice guidance or audio alerts and so on. So there are so many ways. And finally, this particular framework is designed just to make the audience aware how the cognitive radio and AI can fuse among themselves to make an application in the smart healthcare. Okay, moving to the sorry. Well, these are some of the upcoming wireless technologies. I'll not speak much about them. As you can see, the smart transportations, smart. There are so many smart things around the world. So, if we focus directly on our core part, that is the 6G cognitive radio sensor network framework, here we are trying to focus basically the 6G is the driver thing. The 6G is the driving part of the cognitive radio sensor networks where we are doing the communication with everything with a 6G forum. Now here it might be possible the area is small, but we want a high speed, but we want a low latency, we want less error, more a high connectivity. So all this can be obtained by 6G as we all know that. But if we are trying to fuse cognitive radio sensor networks, so what will be the benefit out of it? So this particular part is not related with the smart healthcare, let's say. This is a basic thing to introduce you with CRSN cognitive engine. So basically what they're doing is they're trying to get all the spectrum sensing, all the spectrum analysis. Once the sensing is done, the analysis is been processed and then the decision. So based on the analysis, there is a cognitive radio decision section where it will take a decision. Now, if you ask me what exactly are the decision has been taken, the decisions are very simple. Where exactly I should put the secondary user 1, secondary user 2, secondary user 3, 4, 5, and all that. And again, based on my decision engine, there are few researchers where they are trying to form a cluster based on the decision engine. So I'll give you a brief about it in the forthcoming slides. So let's move forward. And finally, the security module, which ensures the security transmission protects against threats. And this is quite trustable because at the end of the day, if you are trying to implement 6G, we have to be more secure as much as possible because we cannot compromise with that somewhere. And finally, the energy management, because the energy management is also important. As we know, at the end of the day, we are using sensor networks, and when we are calling it as a sensor networks, basically the first thing that comes to our mind is wireless sensors, not wired sensors. Of course, there are so many wired sensors, but there are so many wireless sensors as well. So if we are trying to use wireless sensors, energy management is one of the major important parameter which we have to keep it, because you will feed the battery, you will use the solar power, you will use this, you will use that, but at the end of the day, it is a wireless sensor. So somewhere we have to focus on the energy management as well. What will be the outcome? The outcomes are very simple. If you try to use this particular framework, you will get a dynamic spectrum access. You will get a reliable 6G connectivity. Why reliable? Because you are doing first two steps. So definitely yes. And finally, energy efficient operation. The overall operation will be energy efficient. Well, this is a very general slide again, like why CRSN for consumer electronics. So I think I've explained you already this particular slide. For consumer electronics applications, we have variety of consumer electronics applications, which will include smart healthcare, smart transportation, smart industry, smart home, everything. Wherever there are consumers and wherever there are the things, the implementations, the computations, the calculations, the communications. So yes, it is a consumer electronics application. So yes, at the end of the day, you can use it anywhere, wherever there are communications, especially the wireless communications. You can use the cognitive radio sensor networks in most of the consumer electronics, unless it is a wired applications, of course. Okay, so cognitive radio sensor network for visually impaired users in consumer electronics applications. Now, let us start the overall theme of this seminar with what are the challenges faced by the individuals with visual impairments. So there are various. I have just tried to implement. I've copied some from Google, some from ChatGPT, but at the end of the day, I try to conclude them, and I got this that individual with visual impairments often struggle with navigation and orientations. Basically, they face difficulties in identifying the obstacles, understanding their environment, and accessing the necessary information. So somewhere this was our problem statement where we are trying to do the research and continue it. So identifying obstacles, understanding their environment, and accessing the necessary information. Well, sorry. So everyone will get a query, why CRSN? You can use any, there are so many different technologies. So why CRSN? Well, the CRSN is having some advantages. That is why I'm using it. The cognitive radio sensor networks are advanced networks which utilizes cognitive radio technology. That is the intelligent technology, the smart technology, which use dynamically adapt to varying environmental conditions. So if I need to explain you in simple words, it is such a radio technique which was almost theoretically available since 2000, I think 12, 13. But it has been implemented in some of the industrial purposes as well, but not in a full-fledged because of some of the monopolies of the telecom companies. So that is a different story. Well, so cognitive radio, what they are doing is cognitive radio sensor networks. They are trying to develop sensor networks which will have one network, two networks, three networks, or more than that, and they will communicate with each other in an unlicensed band or licensed band, but without hampering any of the primary user. It is very simple. When you want to use a licensed band, for example, in USA, if you're having some mobile band and you are an unlicensed user, you want to use it. So what you will do? In a basic thing, you will try to think, okay, at night after 12 o'clock or 1 o'clock, the number of users are less, so I can use that channel. Yes, you can do it. But the condition is you should not hamper the primary users. Well, the cognitive radio sensor networks exactly do the same, but here the sensor networks comes into the play with the cognitive radio theme. So basically they enable the device to communicate and share information in a flexible manner, optimizing the use of available spectrum. Now, real-time demands and consumer electronics applications, yes, we have a lot of them. For example, in consumer electronics, I've shown you these particular things, smart home and smart education, smart transportation, and there are so many smart things. So in every sense, somewhere cognitive radio sensor networks will play a vital role. Okay, coming back to the next flow of the topic, that is right now slowly we are moving towards the technical part. AI based approach, cognitive radio sensor network for smart consumer healthcare applications. So what we will be doing next? Well, what we will be doing next. Now, as you can see in the slides, these are some of the framework which we have prepared on our own. We have tried to produce it in a mathematical way, in a very simple mathematical way, and we have tried to prove that yes, our algorithms gives a better results. As well as we went for the simulations, And we have proved again the same thing. So somewhere with this particular methods, we have applied for the patents in 2000, I think 19 and 20, and we got it. So somewhere I thought of sharing this with you. This is quite interesting. So let's start with the algorithm first. So BSS and HML, that is blind source separation and hierarchical maximum likelihood based cluster head positioning. So to make you explain this particular thing in a very simple way is these are the two different algorithms, statistical algorithm to be more precise, which we'll be using for cluster head positioning. Now, please follow this. If just please try to assume this as one cluster, that is when I'm calling it as a cluster, that means multiple sensors in a single positions or a single geometric area. So if this is one cluster 1, if this is cluster 2, if this is cluster 3, 4, 5, 6, and so on. So with this particular algorithms, we are trying to find out the cluster head. Now what exactly is the cluster head? Cluster head is the same one of the sensors among the same number of sensors which will be acting as a class monitor. Let's say the class head. It is as okay. So it's very simple. Cluster head means in one cluster, I should be able to find out one head. So there are multiple clusters. Now, when I'm calling this as a cluster, I'm trying to find it out using the cluster head positioning, because the position of the cluster head, it matters a lot. For example, if this particular sensor node is the cluster head, it is having quite good connectivity with this cluster, this one, and this one, rather than this particular sensor. Okay, I'm repeating. This particular sensor will be more actively selected using blind source separation and hierarchical maximum likelihood method. These are the two statistical methods. I'm not going into deep. So using that method, we are trying to find out the position of the cluster head. So just by seeing, you can easily guess this is the most suitable one. Why? Because this is closer to this is closer to this, and this. So somewhere using these two algorithms, we are trying to find out the cluster head positioning. So this is a simple diagram, of course. In real world, there are so many clusters and the positions are not so uniform. So that is how the thing works. So this is how we are trying to position the cluster head. Now, after positioning the cluster head, what we are doing? We are trying to calculate the power consumption, monitoring, and feedback. So once this has been calculated or once this has been analyzed using this BSS and HML, we are trying to infuse our smartness. And what is our smartness? Our smartness is distributed artificial intelligence. So we are trying to infuse the phenomenon of DAI, distributed artificial intelligence, inside this particular block. Now, how it is working, let us see. Start autocorrelation of two signals from different time instance. For example, from one from here, one from this cluster. Implementation of BSS and PU. PU stands for primary users and secondary users are identified. So when we are implementing BSS and HML, we are trying to do the spectrum sensing. If you remember, yeah. So first we are trying to do the spectrum sensing 3.1 block. Now, then based on all the nodes, we gathered some information and we are smart now. We got some basic knowledge about how to form a cluster. Should I draw this type of pentagon or hexagon or octagon or circle or any type of shape? It doesn't matter. So how to form a cluster? We have that idea. After implementing the BSS and primary users, secondary users are identified. Now, once the cluster has been formed, we are trying to implement the Gaussian copula theory. So what exactly the theory is doing is, we are trying to implement the Gaussian copula theory because all the media, the whole media is wireless. So we have assumed the air is the media and there may be certain type of noises. So how it is reacting to that? And that is why we are using Gaussian copula theory. Now, spectrum sensing behavior of secondary users in single and multiple clusters are analyzed in time varying environment. Of course, the time is getting changed. For example, again, I'm going to the same old example where a user want to communicate with another user, but he is not registered. He's unlicensed, but he want to use the licensed band. So what he will do, he will try to find out a certain time. For example, at midnight 3 o'clock, at midnight 4 o'clock, the channel will be there will be no primary user. So at that time, he can do his communication. So exactly that's the same thing like spectrum sensing behavior of secondary users because that user is secondary users. That he is unlicensed, so he's not paying for the license fee for that particular channel in a single and multiple clusters which are analyzed in time varying environment. So the time is continuously varying, and based on that he's continuously doing the spectrum sensing. So after that the story begins. Now what is the story? That is the DAI applied to each clusters. This is DAI. That is the main fundamental theme, the state of the art of our proposed method. Distributed artificially is applied. Now, what exactly, how it is working? Let's go into a very simple way to make you understand. That is, all secondary users will act as TA. So the TA is your training agent or transfer agent or task agent. So in different papers, they have mentioned different training agent, task agent. So they have different synonyms. So it doesn't matter what exactly TA is. For example, in my paper, I have assumed it as a task agent. We are assuming, sorry, the secondary user will act as a task agent. That means one task will be given to each secondary users. And what task will be given? Wait, please have patience. I'll be explaining you in the next slides. So some tasks will be given in the second for the secondary users, which will be acting as a task agent. Now, this task agent will decide the cluster head, CH, cluster head or cluster heads, which will act as coordinator agent. Now, coordinator agent is a new term which comes under DAI. Coordinator agent means in multiple cluster you can have one cluster head or multiple cluster head depending on the area, depending on the number of agents, or depending on the number of sensors how you are dealing it with. So COA is oh sorry, CH, somewhere the cluster head is a subset of the coordinator agent. Somewhere in most of the applications you will see, and in some of the applications, you will also see the cluster head will also act as coordinator agent. So that completely depends on the application point of view. Right now, at the end of the day, my application is very simple. I am designing all these things for visually impaired person. Well, coming back to the DI part, the task agent will decide the cluster heads, which will act as coordinator agents. Now, forwarding the same information to the coordinator agent and the management agent. Now here how they are dealing with, they are trying to form a correlation communication setup, that is your inter-cluster communication and a resource allocation for secondary users. So basically the combination of COA and MA, they are trying to calculate the overall resource allocation and how they are forming it. So based on this particular output, we are trying to forward the same to the power consumption monitoring and feedback and finally end. That means initially I am getting the information, this yellow thing, I am getting the information from the sensors. I am implementing BSS and HML, and I am trying to form the cluster heads. Among the cluster heads, I am trying to form the task agents, the coordinator agents, and all these things. And finally, based on their replies, their responses, I am doing the power consumption. So that's it. Okay. Now, here there are some more algorithms which right now I'm working on. It's not completed yet, but then that's why this particular symbol. So, start planning agent. So the master agent, the management agent, it performs the resource allocation. As you can see here, the resource allocation has been formed for inter-cluster secondary users. And based on that, we are trying to select the cluster heads. So basically, what we are I'm sorry, the video is on. No.
Hi, Dr. Mukherjee. Yes, we can still hear you.
No, I got some information to turn on my video. Sorry.
Oh,
Fine. Doesn't matter. Ignore it. Yeah, so where were I? Yes, researchers in progress. So we are starting with the planning agent, the master agent, management agent. It performs the resource allocations inside this particular scenario. Let us assume, and we are trying to, based on the output, we are trying to select the cluster head, the detect agent, and finally the MA, the master agent or the management agent. That particular agent and coordinator agent, we are getting a response. Now, based on that response, again we are trying to play the things. How? If the DA can complete the task, yes, no. If yes, then okay, please proceed. If no, then okay, just try to assign the task to another TA because DA is not able. So these type of no scenarios occurs basically on the congested area or in a congested network. In a simple network, we just proceed in this particular way. We don't need DA. Basically, we don't need DA. The work of the DA is being done by TA, and we forward the same thing. And finally, in our proposed work, which we are working right now, we are trying to find out the optimal allocation scheme based on APS. That is advanced PSO technology, where we are trying to formulate the mathematical part of the PSO. As you can see, the distributed, we have got some wonderful graphs. Of course, these graphs takes a lot of time while simulations. So, distributed AI, distributed AI for WSN and IoT. So we are trying to find it out for conventional power allocation, theoretical power allocation, and the simulated power allocation. Now, as you can see, the conventional power allocation, that is quite with the generic formula with the same type of Gaussian noise, Rayleigh fading channel, and all that things. So we got with the simulations, we got the likelihood of getting the correct response from the DAI. This particular likelihood is basically how much we are implementing our technology with the DI and how much accurate it is. So one is the best one, of course. So this is our simulated power allocation, while as the this red line is the theoretical power allocation. So somewhere they are quite close to each other and close to one. So we are quite happy with 12,000 simulations. Of course, somewhere, if as a researcher, if you'll ask me what are the issues with this one, you have got a good graph to show, but yes, there are so many issues. For example, 0 to 12,000 simulations, that looks very good in the simulations part, but not in the real world part, because if a visually impaired person will be facing some traffic, some signals, some complicated scenarios, the AI responses will be quite accurate but late. So we cannot compromise with the delay part, or else there would be some accident kind of thing. So yes, there are some issues with that, and we are working with that in considering the delay. And again, the second issue is, let us assume we are trying to implement some more interesting fancy algorithms to reduce the delay. Will it work? Well, the answer is I'm not sure, because again, it can somewhere it can hamper the error rate, and at the end of the day, the energy consumption. So, being a scientist, being a researcher, we are completely focused on, if we are focusing on the smart application, let's say, we have to focus somewhere in the energy consumptions as well. These are some of the interesting results which we have got with PSO, with DAI, and combining both. So at the end of the day, of course, the combining both will give a better results with PSO and DAI. But somewhere we have to improve it a lot, because still I feel like after zero point 0.1 millisecond, we are getting more responses with PSODI, but it is consuming a more energy. So I've not shown that graph particularly, but somewhere it is consuming more energy, which is not acceptable, because the visually impaired people, they will be using their sticks, they will be using some wearables kind of thing, and it will be having some battery. So if at all we are focusing on the latency, we have to compromise with the energy consumptions. For example, if they are using their sticks daily, so they have to charge it every 5 hours, 6 hours, which is not acceptable again. So somewhere we are playing with that. Well, some more, I got some more ongoing research outputs and discussions. As you can see, there are some simulations and some response time, and response time with DAI for more than 3 clusters, as I've shown you in the previous slides. These are the multiple clusters. So with 3 or more, we'll be getting quite a good results. The response time will be quite less, so I'm happy with that. Sensing time, probability of detection. At the end of the day, the fundamental theory should be very clear. That is, the probability of detection should be as high as possible. So yes, we are getting with the proposed approach with a very less sensing time. So if I'll go back, sorry, I'll go back to this particular slide. So somewhere 3.1 section is working quite good. 3.2 is okay, and 3.3 we have to try to implement it. Some more colorful graphs. So here the task assignment, response time, cooperative cluster communication. So how the clusters are communicating with each other, and how the task assignment responses are. So they are quite um, they're quite colorful and interesting. So as we can see, the simulation, as we are increasing the simulation time, the energy consumption should be decreasing, and somewhere we are getting that with DAI and APS. So yes, this is the red line, and with the simulation time, this is measured in milliseconds. Um, right now, we have got a project. Our university got a project, so we are trying to focus how to reduce this red line further, which is a very key challenge. We are working with a hospital, so let's see how the results will be. And finally, implementing DAI for visually impaired individuals. So yeah, these theories I have already explained. Some of the algorithm where if you want to just try to implement the only the CRSN, so how it will work, just deploy the sensors for each sensor. Will CRSN deploy sensors at designated locations. So the stick, the visually impaired person's stick, and the traffic signal, so they will have the communication with each other in an unlicensed form. That is why we're using CRSN. And if we try to implement the AI on the same, or we can put some AI processing unit. So that's the same thing, basically. Mathematical formulation, simple ones. Yes. This is one new paper which we are writing right now. So, flow of the proposed system is we are trying to do the same thing, the same communication and the computation parts with edge node 1, edge node 2. So, there may be multiple edge. So, how the device is working with the edge networks, because at the end of the day, we are focusing on the consumer electronics applications. Some more simulations, and let's get this. Okay. Finally, the overall theme and overall direction of this presentation is basically to give you an overview of the cognitive radio sensor networks, how it can be infused and how it will impact our social life. Basically, those who are visually impaired, and in a survey from World Health Organizations, around 60 to 70% they are partially blind, and there are some different categories of blind. So everyone have their different needs, their different expectations from the sensor networks, from the scientists and different researchers. So how we can contribute, we have to see in that way. And being an expert in communication and being an expert in computations, we have to fuse both of them to help the society. Some of the references, of course, I've taken some references from Google Images, ChatGPT, etc. And these are the main references. So with this, I finish my slides. Thank you. Please feel free to ask me any questions, audience.
Thank you so much, Dr. Mukherjee, for this very insightful, informative talk and for your time. If anyone has any questions for Dr. Mukherjee, please, you can send them in the chat. You can send them as Q&A. You're welcome to unmute yourself as well and ask questions.
Thank you so much for the presentation. Can you hear me?
Yes, please.
Yeah, so I was just curious about the accuracy of the model itself. It's a very delicate.
Yes. Thank you. Thank you for the question. I've not mentioned it, but the accuracy was close to 85 to 93, which is an issue. Well, we are expecting 97, but the maximum we got with compromising the latency is 93.
Okay.
Well,
because the delicate. I mean, even if
yes,
it is
absolutely.
possible,
Yes,
it should
yes.
be like
You are
99% because of the
absolutely.
situation
You
we're
are
talking
very
about.
correct. That is one of the issues, and that is one of the reasons that we are not able to file a patent, European patent, because we are still improving on that, and we are not happy. So yes.
And how do you deal with I see you talked about offline and on. I mean, how do you sync cases where you have offline situations? How do you sync back to, I mean, when they get online and things? How do you take care of that? Yeah.
Sorry, I didn't got you. Please.
Oh yeah, I was talking about the offline and online situations. How do you manage that?
Online situations.
I mean, like when the system goes offline, for instance, how do you sync the data back? I mean, like, how do you
Okay,
manage?
okay. That's a very good question. I'll get back to you with this particular slide. I don't know which one was that. Where is Edge? Somewhere there was Edge. So yes, with Edge and Fog, we are trying to fuse the information. I forgot. Wait. Yeah, this one. With the Edge node and Edge node 2, and we are trying to fuse a minimum memory. Of course, if there is more memory, they will consume more energy. There will be an issue. At least we are trying to fuse some 500 KB of memory. That would be a lot, of course, 500 KB, but still they have a very less computing power. So with that particular, if they are offline, if the um, visually impaired persons, if they are offline, so that time the edge will take the decisions with that limited amount of memory, and we are trying to focus on the stored memory, which will be acting as a buffer memory, which will store the issues which are not resolved, so that whenever it will be connected to the cloud, so it will be they will update themselves. So we are trying to formulate the same framework.
All right,
Am I
thank you.
clear?
I have a question.
Yes, please.
Thank you so much for actually coming to speak with us today. What made you interested in solving this type of problem for the vision impaired? Because normally those particular populations aren't yet necessarily looked upon to solve the problems because they're a little bit more complex. So what caused you and what was your motivation behind that?
That's a very good question. Thank you. Last almost last 4 or 5 years, when I'm traveling to various countries and all, so I was quite surprised, and I was quite happy to see everything was in particular made for them. Let's start with the roadways, the signal, the different type of dots and all that's there in the signal and all these things. So
Mhm.
somewhere I was quite impressed. And as an expert in wireless communication, basically my expertise is in wireless communication and computations, not in a particular application. So before that, I published some papers with smart agriculture, smart industries. Right now, also I'm collaborating with different smart applications. But with this particular topic, I got fond of because somewhere I thought I have seen them struggling. So
Mhm.
that is a soft part where I got to think really, like being a scientist, being a researcher, how can I contribute to them? So it's quite
Mm.
an observation in a daily life when I'm visiting different countries. No, so I'm not in particular about right now. I'm staying in Czech Republic,
Okay.
so I can see starting from my the daily travel. Let's talk about the buses,
Mhm.
the cabs, everything. That is everything is quite visually impaired people's. They are quite they are doing all the stuff themselves. So
Exactly.
all the things are quite friendly. So I'm very happy with that. So that motivates me somewhere. I've seen these things
I
physically.
appreciate
So yeah.
just saying thank you for the science because sometimes it's more than just the science itself, but giving back to mankind. So thank you.
Absolutely. Thank you. I agree. Thank you.
Yeah, thank you, Dr. Mukherjee. So I should add one more thing. So he used to come US every year. So last year also he visited. Again, 2027 also he is planning to come. So because we are organizing some workshop conferences. So last year also we met in CCNC conference at Las
Yes.
Vegas. So
Yes.
again we are planning to meet again this year. So we are organizing conferences and workshop together, and also we publish some papers jointly. So we have good collaboration with him. We published in a good conferences like including Globecom also. So recently we published a paper on mood detection using AIML. So when a person is talking, what is the mood of that person? That person is taking alcohol, or that person is shouting, the mood is sad or bad. Everything we can detect through AIML. So that type of work actually we published together. So Dr. Amrit is actually very active in research. So he is doing a lot of good work, and especially real-time application, even including healthcare also.
Thank you, Professor. So any further questions, audience? Please feel free to write me if you have any questions. So I guess no further questions. So I'll stop my screen here.
Thank you so much again, Dr. Mukherjee, for your time and insightful presentation. We